Right, students, so we are discussing about big O notation, right? So we will continue with that. So today we will take another example, that is uh, computing the prefix of an array. Okay, so we will wind up, we will finish lecture 1 today. Is my screen visible, students? Right?
Ma'am?
Yes?
Ma'am, you updated Teams, no, ma'am. Can you check?
I updated.
Like noise suppression, ma'am.
Still noise is there.
Like, can you check the option once? Last time we were.
1 minute, 1 minute.
Yes, ma'am.
Hello? Am I audible, student?
Yes, ma'am.
All right, so let me speak. Okay, so you listen first, and then we will see. Okay, whether you are able to get it or not. My screen is visible, right?
Yes, ma'am.
Yes. All right. So we were discussing about big O and growth rate in last class. Okay, so this is what we were discussing. So we used to find the big O, right? Big O rule basically. So this is what we had discussed yesterday. Okay, so the last point that we were discussing was we are going to use the simplest expression of the class. For example, if you have 3n plus 5, you will not call it as O of 3n. You will call it as O of n. Okay, O-N rather than calling it as O-T-N. Is it fine, students? My voice is fine? Is it audible? Is it clear?
Kind of, ma'am. Like, still it is coming slightly. You change, ma'am. Like, that will be, it will be a lot of better. Just the dots and device settings and noise suppression. If you share your team screen, then even we can see. Yes, ma'am. Device settings in the first option. Oh, okay, okay. That's fine, ma'am. I thought after updating that option will come. Hi, it
No,
hasn't come.
that has not come because when I asked it to update, it said that we will update it. So it showed it to me that it is updated. Okay. So let me try speaking loudly. So I think that then it will be clear. Okay. So yeah, so I'll speak loudly. So if it is totally you are not able to follow anything, then you please tell me. Okay. Fine. So what we are trying to do now is we will be discussing the asymptotic algorithm analysis. Okay. So there is let us discuss about asymptotic algorithm analysis, and then we will talk about whether it is related to your worst case or best case or average case scenario, how it is related. Okay, so basically what exactly we mean by asymptotic analysis, right? So asymptotic analysis of an algorithm determines the running time in big O notation. Okay, if somebody asks you the definition, what is an asymptotic algorithm analysis? So we must know, right? So by doing asymptotic analysis, we are trying to determine, what is the algorithm's runtime in terms of big O notation. Okay, now how do we perform asymptotic analysis? You have seen in the last example, what we did was we actually find the worst case number of primitive operations executed as a function of the input size, right? And that function we are going to represent it in big O notation. then this is how we analyze the algorithm. So we have seen the example that we found that array max executes at most 7 and minus 1 primitive operations, right? 7 and minus 2, I think it was 7 and minus 2. So then we say that algorithm array max runs in O n time. Okay, so since your constant factors and lower order terms are dropped, right? So we can disregard them when counting the primitive operations. So we did first example, we did array max, and I asked you to count all the primitive operations, right? So you counted all the primitive operations, and then we calculated the asymptotic analysis, the performance of the algorithm in terms of big O, right? But then we learned that we can avoid we can ignore the lower order terms and the constant factors. So that's what, if we are going to avoid them, we are going to ignore them, we can disregard them when counting the primitive operations. Okay, so with that we will do our next example, okay, where we will not bother for each and every single operation. Okay, so we are going to take an example that is known as prefix averages. Okay, what exactly prefix averages does is, you have two arrays. Okay, you have a given array, for example x is a given array. Okay, and you, corresponding to x, you compute another array a. X is given to you and a becomes the output, such that a calculates the average of I number of elements of x. Okay, for example, if you are having a1, right, a1 is going to have the average of the first two elements, a0 and a1. Okay, so that is what, so the ith prefix average of an array x is average of the first I plus 1 elements of x. Okay, so if you have value of I as 1, right, so I first, I1, so if I is equal to 1, so that means first one, so first I plus 1, first two elements of x you are going to find the average, right? So if you are having, let us say, I is equal to 1, okay? So a1 is going to be x0 plus x1 divided by I plus 1. I is going to be 1, 1 plus 1 is 2, okay? So what you are doing is, you are actually finding the average. Okay, so when, let us say, I is 0, now x is an array and a is also an array. So how do you compute a0? Okay, so a0 is going to be x0 divided by 1, right? It is going to be same, basically. It is going to be same as the first element of array a. So a0 is going to be x0 divided by 0 plus 1, x0 by 1. Right, so first element is going to be same. After that, when you calculate a1 is going to be x0 plus x1 divided by 2. A2 is going to be x0 plus x1 plus x2 divided by 3. So this is the formula to calculate ai, right? So everybody understood, the ith prefix average of an array x is the average of the first I plus 1 elements of x, right? So this is a formula, simple. So computing the array A of prefix averages of another array X has an application to financial analysis. So many times we need to calculate the prefix averages. Okay, in the applications, those are related with finance. Okay, now the question is, it's a very simple exercise, right? It's a very simple problem. But you will see that there are two ways you can solve this problem. Okay, so now also, if I ask you to solve, you can probably say that I have an efficient way by which I can do it. Okay, all of you can solve this problem. It's a simple algorithm, but we will see two algorithms for the same problem. Okay, so this is the first algorithm. Okay, and you will see that we have already said that this algorithm, the asymptotic analysis says that this algorithm's runtime is going to be quadratic. Okay, so the following algorithm computes prefix averaging quadratic time. You see how the algorithm is written. Okay, so please remember this, that we are going to follow a specific notation for writing algorithm. So algorithm prefix average, we are naming it as 1. Okay, and x is the input and also n is the input. All the inputs are given here. right? Then we need to explain that input is array x of n integers and output is array A of prefix averages of x. Okay, so this is one algorithm. Okay, so what it does is it first says that you are going to introduce an array A that is having new array of n integers. X is already given to me, so first you can say I am going to declare or I am going to define array A that is new array of n integers, right? And then for I is equal to 1 to n minus 1, because there are n elements in array x, right? So for I equal to 0 to n minus 1, you are going to do s becomes x0, right? So to keep the sum, so first what you do is you assign x0 to s, and then you apply another, you create another variable that you call as j. So I is 0 to n minus 1 and j becomes 1 to I, right? I is 0 to n minus 1 means you are going to make the index of x 1 by 1, and similarly for j you are going to make j equal to 1 to I. So what you are going to do, s becomes s plus xj, right? So you can see, how it is going to work. So for the first element, of array ai, you are going to take the first element means 0th element, right? You are only going to use x0. Then next time onwards, you are going to add elements, two elements, three elements, and finally you are going to make this ai as s divided by I plus 1, right? So this is the sum that you are using here. And what you see here is you have used two for loops, right? So because you have used two for loops, now how do we see? The first line, when array gets assigned with new array of n integers, there are n operations involved, right? So we are just considering that, you are going to access n integers of array A of an array. So you say there are n operations. And this loop is going to run n number of times. And when this loop runs, for every time the value of I changes, right? Now, see, in the previous case, what we did, we said I equal to 0 to n minus 1. We considered this as one operation. I is assigned to 0. Then we said there are so n number of comparison operations. So in the previous example, we had written 1 plus n. Now I have just written it as n, because we are ignoring the constant term. So we are saying that, okay, roughly there are n number of operations. And every time, the value of, this loop enters n times, so this operation also happens n times. And then for j equal to 1 to I, j equal to 1 to I, now if you see I is equal to 0 to n minus 1, you make j is equal to 1 and then 1 to I, right? So j equal to 1, then you are going to do a comparison operation, right? And when you find that j has not reached to I, those many number of times you are going to perform the comparison operation. That's why you are saying 1 plus 2 plus like that. So first time j is equal to 1, you have written this one operation. Then you have to check j, j is less than I or not. So 2 times you will get that comparison, right? Next, so 2 times is 1 when j becomes 1, So 1 is, we had discussed in the previous case also, when j becomes I, j will become I, still you will have to do the comparison, right? And you will find that j is not less than I. So next time, so first time you will do one comparison, next time you are going to do two comparisons. First time, sorry, you are going to do one assignment, next time you are going to do two comparisons, then three comparisons like that. Finally, you are going to do n minus 1 comparison. So this loop is going to execute, every time based on the value of I, this loop will be executed. Firstly, it will execute one time, then two times, then finally it is going to be executed n minus 1 time. So accordingly, this operation, s becomes s plus xj, will be executing correspondingly these many number of times. And finally, what you are doing, so this part is inside this for loop, right? So this part is inside this for loop as per the indentation. And when you come out from this for loop, okay, from the inner for loop, then you are going to assign ai becomes s divided by I plus 1. So this line will be executed n number of times. And finally, when you say return a, then you are going to execute it as one time, right? So now when you calculate that how many number of times you have done this operation, right? So what you are going to do, n plus n plus n plus this plus this plus this plus this, right? This is roughly because we have still ignored some of the constant terms. So how it is going to come as? It is going to come as quadratic. Why? Because if you make this all n, you can roughly say that it is 1 plus 2 plus n, you can say, right? Sum of first n natural numbers. So now if I going to count all these terms are n, right? So roughly I can say that I get a summation as 1 plus 2 plus n plus dot 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 till n times. Okay, so that is sum of first n natural numbers. Right, so I can say that the running time is O of 1 plus 2 plus n, right? So sum of first n natural numbers is n into n plus 1 by 2, right? So it's an arithmetic progression. Okay, so you know that the algorithmic complexity is O(n) square. You could have simply said that, ma'am, I know because there are two for loops, one loop inside another loop, so I know that it is going to be n square, right? So all of you know to apply that. Okay, so now can we improve on this algorithm? That is the question. Can we find a better algorithm than this to compute prefix average? Definitely, right? We can find, you know the problem here, why did we get the algorithmic complexity as n square? You will say that there are two for loops. If I can use only one for loop, that would have been enough. Right, fine. So is there a way that I can use only one for loop, or what is the problem in this algorithm? We will never say that this is a good algorithm. This algorithm is all fine, works perfectly fine, but it is not an efficient algorithm. Why? What is the basic problem in this algorithm?
I'm recomputing it again and again. Like
What are we computing again and again?
the sum,
Very good. Yes, yes, yes. So that is the problem in this algorithm. So good that you should identify. The problem is this line. S gives you x0. So every time when I become 0 to n minus 1, we are doing this operation. That we are again starting from the scratch. Again we are saying x0 goes to s, and then for calculating average, we are doing sum of those elements. So when I am calculating A3, I am calculating x0 plus x1 plus x2 plus x3 divided by 4, right? So what could be a better solution, that if we can keep this running sum somewhere. So if I have already performed a summation till A3 elements, let me store it somewhere. Next time I just add A4 and divide it by 4, right? So that is the key. So we will do that. So this is another algorithm. So that gives you a linear time complexity for the same problem, right? Prefix average to xn, array x of n integers, output is array a of prefix averages of x. So this is how we do. Same, first step is same. A gets the new array of n integers, and then we make sum as 0, right? We make a variable sum as 0. It takes only one operation, and then we do for I equal to 0 to n minus 1. S becomes S plus xi. Every time we need not calculate that sum. So initially S is 0, so S becomes S plus xi. And then you make these two lines are inside this for loop. Ai becomes S divided by I plus 1. So this will keep on calculating because you are having this running sum. We call it as a running sum, keeping a running sum. Okay, so this is going, now if you calculate roughly n operations, one operation, roughly n operations. So you can call this as there are totally n plus one operation. Plus, if you count that incrementing of I becomes I plus 1, right? 2 into n minus 1. So we are not considering that. Okay, so roughly n and n operations. So now if you calculate, you are going to get the algorithmic complexity as big O of n, right? So you saw one example that both will give you the same answer, but you saw the difference in the time complexity. Fine. So all of you know all that, right? So that was the introduction of the course, that you already have gone through all these things, right? You knew all the rules, but we must understand that what are the basic operations involved. And somebody asks you in your in your exam or placement, you must know that you are going to ignore the lower order terms, or you are going to ignore the constant, but you must know that okay, What are the basic operations involved in that? Okay. So now, and in this course, we require some mathematics as well. Okay, so I have written here specifically that you need to review section 1.2 of your textbook Goodrich. Okay, so that much of math you need. If you read that, that is more than enough actually. So the math is about summations, some rules, what is the sum of first and natural numbers, or if it's a geometric progression, what is the, there are conditions, what is the sum of that. All those things you should go through. And then you should also go through logarithmic and exponential. You must go through these techniques and you must understand basic probability. Okay, so you would have done this very nicely, in all these things you would have done in your 11th or 12th, or when you were preparing for your entrance examination of engineering, right? We know a lot of maths at that time, logs, everything, trigonometry, so many things, but we forget once we join engineering, because we don't use it. That is how the probability and all, we would have read one full book, all kind of probabilities, conditional probability, this, that, but we would have forgotten now. Okay, so whatever is there in section 1.2 of Goodrich, please just have a review. Again, you need not go through in depth, but sometimes, if you want to prove a particular, you want to basically converge to a solution, that time you may need that kind of a math, right? And whatever is important, I have also put it in my slide. So I have copied from the book and put it, made a copy and pasted it here in the slides as well. Okay, but whenever you find time, please uh, read section 1.2 of the textbook. Okay, so just to revise few of the concepts, I have put it here. Again, this is from the book only. Okay, about logarithms and exponents. Okay, we already know that when you say a is equal to b to the power c, we can also represent it as log a in base b is equal to c, right? Or if it is given log a in base b equal to c, that means a is equal to b to the power of c. Don't forget this. Very simple principle, but we forget. Hmm? So, and you must know that, as is the custom in computing literature, okay, we omit writing the base b of the logarithm when b is equal to 2. So whenever you say LG, you will also see not log, you will see LG. LG also means base of 2, or if it is written log without any base, we will consider it as base 2 throughout our course. Okay, so if log is written without any base, please understand that we mean it by log base 2. So you must know that log 1024 is going to be 10, because 1024 is 2 to the power of 10. Okay, then there are number of important rules for logs and exponents, including the following. Okay, so I have just put some of the rules here. So that is theorem 1.14 in your book. Okay, so what are those rules? Okay, so let a, b, and c be the positive real numbers. We are assuming that a, b, and c are positive and they are real numbers. Okay, so we have log AC base b is equal to log a base b plus log c base b. All of you know that two numbers are multiplication, a into c. So this is going to be log a plus log c. Okay, another rule, again, all of you know this, log a divided by c base b is log a minus log c, right? Then log a to the power of c base b is c into log a to the power base b. Okay, now this is important. Rule number 4. What is this? This is about changing the base. Log a to the base b, right? So I am changing the base. It is required sometimes to calculate when it is given log a to the base b. I say log a to the base c. I change the base of the log from b to c divided by log the old base to the new base. This is the formula. Log a to the base b is log a to the base c. C is a new base divided by log b, the previous base. The previous, the b was the previous base, log b base c. Right? So the rule number 4 is important, that we use many times. Then another theorem is b to the power of log a base c. Okay, b to the power of log a base c is a to the power of log b base c. You can prove this. So how do you prove it? You take the left hand side and then you use the, you take log at both the sides. You use changing the base, and then you should reach to the right hand side. That is how you prove. Log a base c is equal to b to the power of log a base c is a to the power of log b base c. Okay, then this is another rule of algebra that you already know. B to the power a to the power c is b to the power ac. Another rule of algebra you already know. B to the power a into b to the power c is b to the power of a plus c. And this rule also you know. B to the power a divided by b to the power c is b to the power of a minus c. So rule number 3 and rule number 3, 4, and 5 we tend to forget, but we may have to use these three rules. We should not forget. Okay, another thing, another important notation. Okay, so if I want to write log n whole to the power of c, right? Log n whole to the power of c, we represent it by like this: log to the power of c here n to denote this function. So this is a common notation you will see in book. So what is log n to the power c? So if it is written like this, log c n means it is log n whole to the power of c, right? So c can be any positive number. So you can often see that log 5n means it is log n to the power whole to the power 5. And again, we are going to use log of log n. That means log of log n. Okay, to represent, you will see that log n, log of this log n can also be written as log of log n. And you will also see many times lgn. Lg means for base 2 we are also using the term as Lg. Okay. So then another, now there are, there are some more, you can say some more results. You get, some more results. You can make them as results or you can keep remembering them. And you have got these results by using the previous theorem, that is theorem 1.14. So these are the basic rules. If you apply them, you are able to get all these new theorems, you can say. So again from the book, it is example 1.15. We illustrate some interesting cases when the base of log or exponent is 3. Okay, so the rules cited refer to theorem 1.14. So theorem 1.14 is in the previous slide. We are going to use 1, 2, 3, 4, 5, 6, 7, 8. These 8 rules to get these inequalities. These things which you can prove. Okay, so for example, log of 2 and log 1 is going to be this, right? So you have actually applied rule 1 twice. So it's actually multiplication. Log 2 and log n is log 2n plus log of log n, right? Again, you have said log 2n is log 2 plus log n. So log 2 is going to become 1. That is how you have got this first expression. Okay. Similarly, log n by 2 is going to be log n divided by log 2. Right? Log 2 base 2 is going to be 1. So this is log n minus 1. This is by rule number 2. In the previous slide, those 8 rules are given. Log of under root n is going to be log n to the power of half. So which is going to be 1 by 2 into log n or log n by 2. Simple. Then log of log under root n. Right? So this we are going to make it as log under root n is log n to the power half. Right? So it is going to be log n by 2. Right? So you can also call it as log of log n minus. So this is log of this whole thing. Right? Log of log n minus log of 2. Log of 2 is going to become as 1. Right? Now, do you understand this one, students? Log n to the base 4, n to the base 4. Are you able to get this? Apply this one. So what are we doing here? Log n to the base 4.
Changing the base, ma'am.
We are changing the base, yes. So we have made log n to the power base 4 is equal to log n to the base 2 divided by log 4 to the base 2. So log 4 to the base 2 is going to be 2. So log n divided by 2. Okay. Then log 2 to the power n becomes n by rule number 3, and 2 to the power log n becomes n. Can you understand this? 2 to the power log n becomes n by rule 5. The rule 5 was this. A to b to the power log a base c is a to the power log b base c. Okay, so when you apply rule number 5, you get this 2 to the power log n base 2. 2 to the power log n base 2 is n to the power of log 2 base 2. So that's how you get n by rule 5. 2 to the power log n is equal to n to the power of log 2 base 2. Log 2 base 2 is going to be 1. So by rule 5, you get this. So 2 to the power log n is equal to n basically. Okay, so this is a very important formula. Sometimes you are stuck, you are trying to solve the complexity, you get it as 2 to the power of log n. But I do not know whether, this is my, so what is the complexity, so if you say, what is that? It is not polynomial, it becomes exponential, no? So if power of some constant is 2 to the power of something is that is called as exponential, right? You know that. So if you let us say you are solving you are solving some asymptotic analysis and you are stuck with 2 to the power of log n. So what should you consider it is? It is actually linear because 2 to the power log n is n by rule 5. It's actually linear, but I am thinking that this is an exponential term, right? So that is why you must understand this simple little maths is required, right? To reach to the final solution, to converge my solution, I need to know these transformation in my fingertips. These transformations should be there in my fingertips, right? So the viva that you face, maybe I mean to say in your placement exams, if if really they ask you the complexities like this, so you need to be really quick for that. Okay. Then let us say you have another rule. 2 to the power of 2 log n is equal to, already it is solved, 2 to the power of log n, you can say this is square. 2 to the power of log n, you can actually multiply this as square, right? And you already know that 2 to the power log n is n. You have just solved it. So this is actually n square. This is actually n square by rule 5 and 6. So you can actually remember like this, that log 2 to the power n is n, right? Log 2 to the power n is n. That you know already, that you will just take it is n log 2 base 2, so it is n. 2 to the power log n is also n. And 2 to the power 2 log n is actually n square. Okay, and this one, 4 to the power of n, can also be written as 2 to the power of n to the power of n. So we can also say that it is 2 to the power of 2n. 2 to the power of n can be 2 to the power of 2n. Simple. Okay. These transformation where exactly you may have to do. Okay. So one, I told you that you are doing the algorithmic analysis and you want to converge to a solution. Sometimes you need to compare, right? So this is just a game of comparison, right? How I can say Fn is theta gn, or Fn is O of gn, or Fn is Fn is less than or equal to C of gn, or Fn is, or gn is greater than equal to some amount of Fn, or Fn is greater than C of gn. So that time you may require this, right? Sometimes you are feeling that this is less, but actually both the things are meaning the same thing. Alright, so now 2 to the power of 2, sorry, n square, 2 to the power 3 log n is nothing but n square into n cube. Why did I say n cube? Why the same analogy? See, 2 to the power of 2 log n is 2 to the power log n is n. 2 to the power of 2 log n is n square. Similarly, 2 to the power of 3 log n is n cube. So n square into, this is nothing but n square into n cube. So that becomes n to the power of 5 by rule 5, 6 and 7 of the previous slide. Okay. Similarly, this is again very simple. 4 to the power n divided by 2 to the power n. You can write this as 2 to the power of 2n divided by 2 to the power of n. So this is actually, you are going to get it as 2 to the power of n. Simple transformation sometimes help to compare two complexities. Right? When you want to compare two complexities, you may require these kind of transformation. So please go through this. So, most of the important things I have covered here, but you should go through, that section of, I told you that section 1.2 of your Goodrich book, the textbook. Okay. Or part, L1 analysis of algorithm part 1. Okay. So we will start with part 2. So I have written here analysis of algorithm part 1 remaining to be done later. So there is something, it actually talks about, in this part 1 remaining, I have talked about all other notations, small o, big o, small omega and all those things. But I don't want to have a confusion here because big O is most important. That is what we discussed. We will also discuss theta and omega next. Okay. So that is what I have made as part 2. Okay. Yes. So now we are done with the introduction of the subject students, right? So we know what is an analysis of algorithm, how do we compute the basic operations, which we also call as primitive operations, and based on the primitive operations, uh, we actually compute the number of primitive operations in the worst case scenario, and that is what we represent. The number of primitive operations, those will be applied in worst case scenario as a function of input. Okay, that is how we analyze the algorithm. Okay, so there are few things, which as as a matured computer scientist, we need to answer it like that. If somebody asks me what do you mean by algorithm analysis, I should not say that algorithm analysis means big O notation or something like that. Right? I should have a proper definition. Okay, so that shows my maturity in the subject. Right? So please say it. So sometimes in computer science, we also need to know the definition. Any subject where maths is related, you need to understand it based on the definition. You may know everything, how to calculate the asymptotic analysis. Why do we do asymptotic analysis? But where definitions are required, we also must be able to define it. Okay, so asymptotic mutation. Okay, so how do you answer the question? What is the running time of algorithm X? Right? That is for that sake only you use the asymptotic notation. So we need a way to talk about the computational cost of an algorithm that focuses on the essential parts and ignores irrelevant details. Okay, and so you will see, when you write actually big algorithms. Okay, so there will be very very big algorithms, wherein some part of the algorithm will be most important. That is a part which actually runs most number of buttons. Okay, so if you had in your compiler design course also, you would have studied something like this. That a program is given to you, or in your the courses where you talk about memory, there also you would have studied. There is an algorithm, there is a code. Algorithm means, let us say there is a code associated with the algorithm. But most of the time, what happens that 80% of that code executes most of the time. Right? You can analyze this, or if you have not analyzed, you can see that whenever you write an algorithm, or let us say you write a program, it's a big program, but you will see that only 80% of that program is executed most of the time. Right? So let's say there is some initial part, right? Initial declaration part, something that executes, maybe one time. And then let us say there is a for loop. All right. And you are running that for loop, let us say 10,000 times. So that part of that portion of the code is actually responsible for your asymptotic analysis, isn't it? And then towards the end, you are going to return from the function. So that portion of the code also runs only one time, right? So that 80-20 principle applies everywhere, students, even in algorithm writing, right? So most of the time, my 80% code is responsible. So I should make sure that when I'm trying to do the optimization, code optimization, or if I want to write the code efficiently, I have to focus on that portion. Okay, so if I want to improve on, maybe the portion which is executed very less number of times, it won't give me that, it won't give me, the results, as how I have made the changes. Okay, so we need a way to talk about the computational cost of an algorithm that focuses on the essential parts and ignores the irrelevant details. Okay, so you have already seen some of the complexity. You have seen linear kind of complexity. You have seen n log n kind of complexity. This is not linear, linear multiplied with a logarithmic component, and then you have also seen n square kind of complexity. You have seen all kind of asymptotic notation, right? So precisely calculating the actual steps is tedious and not generally useful, right? So different operations take different amount of time. Even from run to run, things such as caching, etc. causes variation, right? If you actually start measuring the time, you will realize that every time different runs are giving you different amount of time, because there are many things involved. You know about something called as caching, right? So maybe first time when you are using, so suppose you want to do the previous example we saw, sum is equal to sum plus xi, right? So first time maybe when sum is brought from the main memory, it takes more time. But next time onwards, sum is already there in cache memory, so it may take less time, right? So it depends from run to run and what kind of memory you are using. So it is what kind of hardware software you are using. It is going to be different. Okay, so we want to identify categories of algorithmic runtime. Right? So why are we learning asymptotic notation is, basically to calculate, to see the, what is the behavior, what will be the behavior of the program with respect to the number of, when you change the number of inputs, when you change the input size. But we also want to categorize different algorithms based on their runtime, right? So for example, a question is given to me that f1n takes n square steps, right? And f2n, that f1n means f1 is a function, f2 is another function, f3 is another function. So first function takes n square steps, next takes 2n plus 100 steps, and f3 takes 3n plus 1 step. The question is, which algorithm is better? So obviously you will say that n square cannot be better, right? So obviously 2n, anything, f2n or f3n will be better than f1n. That is what you will say. So the next question is there a difference between f2 and f3? Now it is a difficult question to answer, right? You will say depending on the value of n. If n is quite large, you will ignore this 100 also, you will ignore this 1 also. Then I will say that then which one is better, 2n or 3n? Now if n is quite large, 3n is, so now if let's say n is 10,000, so 3n is going to be 30,000 and 2n is going to be 20,000. Right? And then, but you, so should we say that 3n plus 1 is better than 2n? Right? So that's a difficult question to answer, right? So to ignore such situations, that's what we are doing. We are saying that we will assume that we will drop the constant term. We will say 3n is also n, and we will say 2n is also n. Like that we have already made this assumption, right? But if somebody asks me, obviously, 2n, if n is 1 million, then 2n is going to be 2 million and 3n is going to be 3 million. Should I really avoid 2n and 3n? That's the question, right? So, but with lot of experiments, it has been found that when n is really high, when n is small, it really matters. When value of n is small, yesterday I showed you the plots, right? When value of n is small, with small input size, the plots are different. They are not really linear. But when we assume that n is very, very large, very, very large, they almost tend to become the similar. So then we are going to ignore them. Okay, so is there a difference between F2 and F3, whether this difference is important or it is significant? Those kind of questions we must understand, right? So sometimes what happens, I just want to tell you these things, students, because all of you are preparing for your project. Sometimes what happens, you are trying to show a very small difference. You are comparing two algorithms, okay, and the difference is, let us say, one is giving you a a improvement of 0.56. So there is a difference 0.56, and another one is 0.58. Now will you really say that 0.56 is better than 0.58? That's a research question, right? So you will say that I have got it 0.56, so I am much better than 0.58. But how much better you are? Okay, so you need to understand that as a computer science algorithm analysis student, you must understand that when you say I am better, with which degree you are better. And are you better every time? Let us say if there is a difference 0.56 and 0.58, the difference is just 0.02, right? It's just 0.02, which is not very much significant, the difference is. And will you get this much difference every time? Okay, so you need to think in those terms now. Okay, so this is what, students, I think we will continue with this in next class, tomorrow's class. Okay, so yeah, so we will be discussing big O, and from big O we will see some of the proof techniques tomorrow, and finally we will conclude tomorrow with big O. We will also talk about big omega notation tomorrow. Okay, so that's it, students. We'll wind up for today. Okay, so you tell me, where you could you understand, students? Could you understand, or it was really disturbing?
Yes, ma'am, we were able to understand and make a, like it was proper only, not so disturbing.
Okay, thank you very much. Thank you very much. So we will meet tomorrow, students. Thank you. I will wind up the meeting. Yeah, yeah.
Thank you, ma'am.
Thank you.